So there is not much I have to say on quantum turbulence, but I want to make some, to give some information, things which you will put into the method section or whatever supplementary material, perhaps, about the methods which are used to typically to simulate numerically this quantum turbulence. So a start, actually, we'll see from Landaus equation, because they fail, because they don't contain vorticity, the quantum vorticity. And then I'll try to show you that we have a situation which can be improved a lot, in the sense that unlike the case of the Navier-Stokes equation, compressible or incompressible, for which we have an equation of motion to solve analytically or numerically, in this problem we have only some kind of short blankets which don't cover the entire body, but they work in some areas, and some connect to each other, but only partially. And essentially, they can be classified in this fashion. It is a bit as if you can imagine that a tree is a vortex, long and thin. So if you go very close, you will see the details of the bark. So you will know, you will try to determine whether the vortex core is hollow and what's the density profile, or suppose it is not hollow, what's inside. So this is the micro scale, and typically it is described with its own limits by the Gross-Pitescu equation. Then there is some kind of mesoscale, in the sense that you move away from an individual tree and you start seeing many trees, but you don't see the bark. You don't see the bark of any tree, you just see sticks. So you count sticks and you see essentially that you perceive that you are inside a forest. And then there is another scale, macro scale, say, for the fun of it, where you don't see the individual trees because you are farther away. You only see whether there is a high density of trees or a lesser density of trees. So you see dark green or light green. So that's a situation, more or less. That does not mean that one can try to do some very intensive calculations. For example, some pictures are shown by Marc Brachet yesterday, and some pictures shown this morning gave the details of the bark of an enormous amount of trees. So it doesn't mean that the GPE is not good enough to capture many, many trees. But more or less, that's the spirit of what I want to say. Distinguish these scales. And if you want to look at some kind of key papers, I would say the original paper by Hall and Vinen for the description of the forest, the paper by Caroline Noor and Brachet about the use of the Gross-Pitescu equation for turbulence, because really it made a big effect. And also this paper by Tsubot and students and Nemirovsky about essentially giving the same result as the Gross-Pitescu equation, producing the Kolmogorov spectrum, at least approximately, for the other method, the method of the mesoscales. But let me start from the Landaus equation. So the equations were written in the 40s, and they explain all phenomena, essentially, which were known, provided velocities or heat fluxes were small. So provided there were no vortices, but vortices were not known yet. So I don't repeat the equations. I just want to make an example. So the example, classical example, the first quantum turbulence system studied, thermal counterflow. So you have a channel, as I said the other day. You dissipate some heat flux at one end, and there is large helium bath at the other, and you produce a relative motion of the two fluids, which is proportional to the applied heat flux. And if you take the Landaus equation in a steady state, very simple, you will see something like these two equations, and you can try to solve them. So, roughly speaking, what do we see from these equations? Well, from the superfluid equation, you can connect the temperature gradient and the pressure gradient, gradient along the channel. My gradients here are only along the channel because across the channel, there is the problem of the boundary conditions, which essentially we don't know really. Then you can also see, by summing the two equations, you can eliminate the term with the gradient of the temperature, and then you find an equation of motion for which links the velocity and the pressure gradient, which is this. Now, that's quite nice because it's exactly the same equation which exists in a textbook of fluid mechanics. So that you can solve in a channel flow or in a pipe flow, and you will find if the profile of the velocity given the applied pressure gradient, and perhaps you want to calculate the average velocity across the channel, so without looking at details about the boundary conditions. So this kind of average velocity would be proportional to the pressure drop along the channel. There will be the viscosity there will be the size of the channel, or I put a factor C essentially to account for the geometry, because you may have a square or circular pipe, whatever. So you relate the pressure gradient to this average velocity and the size. Okay, fine. And from this, from the first equation, then you can recover the temperature gradient in terms of the average velocity of the normal fluid, here and there. And you know that that is proportional to the heat flux. So, in the Landaus equation, we have this perfect heat conduction, and you produce a temperature gradient and a pressure gradient proportional to the applied heat flux. And that is because you are in this channel situation. Now, that is only good if the heat flux is small, which means if the counterflow velocity is small, because if it exceeds some very small values, actually, then you start creating vortices, which you will detect using other methods, for example, second sound, etc. But what do we get? Okay, so imagine now we have these vortices. Now the vortices will induce an exchange of momentum between the normal fluid and the superfluid, which is called mutual friction, because it is a friction on the two fluids separately. So there is a plus and a minus, as you can see. So there is a plus here in the superfluid equation and a minus in the normal fluid equation for the same force. And I put some kind of brackets and the subscript turbo to say that here we're dealing perhaps at the best, if we try to use these equations, we should think that we are integrating across the channel transversally and perhaps making some time averages or whatever, because the situation is turbulent. Still, what do we learn from these equations? Well, we essentially proceed in the same way. We'll find, first of all, that you can actually, you see, if you sum the two equations, then you get rid of the friction, F, and you cancel out also the temperature gradient terms. Those temperature gradient terms, which in the low velocity case are responsible for the famous fountain pressure effect, if perhaps you heard this name. Okay, so we are left with the same relation between, essentially, the same relation as in classical fluid mechanics, again, so the Laplacian of the velocity of the normal fluid, and then there is a pressure gradient. Now, it's the same equation, but the situation is different. So we can actually be tempted, guided by the experiments, to say that since we have the same equation, perhaps essentially the pressure gradient in the laminar case and the turbulence case are the same. So that must be more or less true. Once we have established that, then we can find the temperature gradient in the turbulent case, and you see that it's equal to the temperature gradient in the laminar case with a correction, and that is where the friction comes in. It's the added temperature gradient. So, by measuring temperature gradients along the channel, we recover information about the friction, provided we know what is this basic laminar flow situation. And here the problems start. So historically, there were two Dutch physicists who, starting doing experiments, they realized that the data essentially can be understood, or fitted better than understood, by assuming that this friction has to do with the cube of the counterflow velocity. And they introduced an arbitrary coefficient. They call it A, because A is the first letter of the alphabet, I imagine. Hall and Vinen, after that, developed their theory of mutual friction, And they were actually doing somewhat a different experiment, and they introduced another coefficient, and they call it B. I think actually it's called B. It has been called since B because A came first. So you see anyhow the dependence, okay? But here there is also the vortex line density. So the vortex length per unit volume, L. So here we have VNS, which is the counterflow velocity, if you want the heat flux, cubed. Here we have L times VNS, the vortex density times L. Okay, so what do the experiments say? So in the laminar situation, subcritical heat fluxes, indeed, it is true that the pressure gradient is always more or less laminar in the heat flux. So you see this line, okay, changes slightly the slope, but there is not a significant break. So our approximation was valid. It is actually the temperature gradient which is more sensitive to the transition from laminar to turbulence with vortices. The break is much more marked. So we reach this critical velocity, then we deviate from the linear law, this curve leaves, and then seems to deviate more. You may ask me why there are two values there. This is actually a complication due to the fact that you don't recover exactly the same values when you ramp the heat flux up and then down. There is some hysteresis in the problem. But in any case, don't be misled by this part of the graph. What matters is that here, the temperature gradient is much larger. Okay? So that is how the friction, which means the presence of the vortices in the extra dissipation, manifests itself. So it does not cause large pressure changes, but it does introduce significant temperature changes. So there was also another way to describe the situation, which was introduced by Vinen, which is the following. He wrote some kind of master equation, really, for the vortex line density, how it can change with time. L, the vortex length per unit volume. The volume typically is fixed in those experiments. He argued that essentially this DLDT was the balance of a generation term and some destruction term. And he came up with some forms of this generation term proportional to the relative counterflow velocity, VNS, the vortex line density, L to the power 3 over 2, which is something which he could observe using second sound, and then a destruction term, which is the second term. And then he found immediately, he moved immediately to setting DLDT equals 0 to recover the steady solution, which here it is. So the vortex line density is proportional to the square of the counterflow velocity, which means the square of the applied heat flux. So that is actually, okay, this equation has been useful in a sense, although some may say we have not really discovered something deep, because this relation, actually, you can actually recover it from dimensional analysis only. And in any case, you don't know gamma. Why? Because it's the ratio of two order 1 constants, chi1 and chi2, which you see in the generation and the destruction terms, which perhaps order 1, but what's the ratio exactly? So essentially we're stuck. We have to move on, and we have to think of models. Models for the friction, guided again by the experiments. So as I said, the Grosspitescu equation is one of the models. It was introduced much later, of course, and you've seen it many times in the last few days. Here it is written again. So let me stress, I want to stress not the actual methods, but how they compare to each other and what are the limitations. So this equation, we know, describes a weakly interacting gas. And the temperature must be very small, because ideally it's a 0 temperature limit. So in many situations, it is actually a very good quantitative model of the behavior of such an atomic gas, okay, at low temperature. And we know that it accounts for a variety of phenomena, which is actually striking. So there are vortex solutions, straight vortices, or even knotted vortices, or even numerically tangled vortices, as you've seen. there are sound waves, as you've seen. I don't think anybody has talked about nucleation. There is the problem of how to create the first vortex. That's called the problem of nucleation. Yes, it can be done. This equation nucleates vortices. The Euler equation would not. We have seen many times that it describes vortex reconnections. It accounts for boundaries very well. So all sorts of nice things. Unfortunately, the assumptions are not really very close to what happens in liquid helium. Okay, so we are a bit far from liquid helium. So why do we compare it to a liquid? Because hidden inside that equation, using the famous Madelung transformation, there is it has been shown this morning, there is actually the Euler equation, which is written there with an extra pressure-like term, which people call the quantum pressure. So it's a term which contains Planck's constant, and which one can see becomes small if you look at very large length scales, much larger than the Healing length, where the Healing length you can estimate it from the ratio of the kinetic energy term, which is the term with the Laplacian, and the cubic nonlinearity. So essentially we have hidden here a compressible Euler equation plus this extra term. Now this extra term, which is actually what makes the difference between Euler and a superfluid. The vortex nucleation, the vortex reconnections, all those good things. So, but as I said, it's not liquid helium exactly. Okay, so we think that we can use it, but it will guide us only in a qualitative way. And the most famous, most noticeable thing, which you've seen a slide of, you've seen actually the dispersion curve arising from this equation. So there is a phonon. It starts off at low wave numbers with phonons, so it's linear, sound waves, and then it tilts, you get free particles. There is no sign of the famous Roton gap, the Landaus spectrum. It's not there. Okay, so let's consider then the second model, which is the vortex filament model. So this model actually was invented by Klaus Schwartz, working at Chicago and then IBM, on the ground of this idea that in the experiments, they knew already that they had quantum vortices, and they could estimate how many, so they could estimate the distance. And he thought that, he realized that the separation between vortices was vastly larger than the Healing length or vortex core size. And typically, there are, for example, at least 4 orders of magnitude. So vortices are really thin sticks. And there is in time nice mathematical topic, which is the theory of space curves. So vortices can be approximated as space curves. That is the idea. And you see here, so he started calling the vector S, the position along a vortex line, which is described parametrically by this Greek letter zeta, which means arc length. So you take some initial an origin, and you measure the length along the arc, and then you proceed, and you can write all the equations, the beautiful equations for space curves, and this configuration will change with time. So the question is, how does it change with time? Well, let's look at the details a bit more. So S is the position. So if in red we have the vortex line, so with the flow, quantized circulation. So take a position vector, and there you can define 3 unit vectors. One is the tangent unit vector, S prime, which is how this position vector changes with arc length. So that, it turns out it's a unit vector. If you take the second derivative, you get a quantity whose magnitude, a vector quantity whose magnitude is the inverse of the local radius of curvature. So if the line is actually curved, if it is a small vortex ring, this capital R is small, so this is very large, this S double prime. And for a straight vortex, you have an infinite radius of curvature. Okay, so this is not a unit vector, but you can normalize it and define a normal unit vector, which is actually this. And then you can construct the third missing unit vector by taking the cross product of S prime and S double prime. It's not going to be normalized. And that vector will be in the direction of the binormal. Okay, here it is. So we have these three unit vectors. And so the next task is to write an equation of motion for the vortex line, and then find out how to solve it. Indeed, like it happens, for very simple configurations, you can actually do some analysis by hand. But of course, Schwartz wanted to do some calculations of turbulence, so he knew that he was going to face it numerically, and that is why he was at IBM, to use big computers. And the numerics is done in a Lagrangian fashion. That is to say, the vortex line is discretized in great number of points, and then there are techniques for this. So this discretization, for example, is not uniform. You need clearly more discretization points where the vortex lines are particularly tight. They make, you've seen in some plots this morning, the vortex line making tight loops, and there you need lots of discretization, otherwise you lose the resolution. You want to keep the resolution uniform, okay? So that's okay, but we're not going to say anything about that. So the question is, what is the equation of motion of this space curve? So Schwartz then continued, and he argued along this line. So essentially, the vortex is very thin. At that time, it was not clear whether the vortex was hollow or empty or filled with something. The various models were conjectured. In any case, it is very, very thin. So he thought of writing an equation of motion, like Newton's law, but neglecting the mass of the vortex line. Okay, I stress, this is not a mathematical vortex line. It's actually a physical object. It's actually a depleted region, okay? So neglecting the mass, we're left with the force equal to 0. And so that is how the vortex line behaves. So it does not behave like a particle. Essentially, it's always reacting. It's always in equilibrium. It's always balancing forces. Now, here the forces I'm going to write as a unit length of superfluid. So which forces act on the vortex line? Well, there are two forces, in principle. One force is the Magnus force. Oh, this is not good. This is too tiny. So the Magnus force is this Fm, and you know what it is. So I remind you. So if you have, classically, if you have an object around which there is a circulation, then there is this strange transverse force. And somewhat a simple interpretation, which it's easy to think of, is that imagine there is actually, you see the vortex, which is, the core is that violet-purple region. And so there is a circulation which is clockwise, and there is also some flow past the object with the circulation, which is our vortex. So clearly, on one side, the bottom side of the vortex, you see that the velocity of the circulating fluid is opposite to the velocity of the incoming flow from infinity. On the top side, actually, it's in the same direction. So you're going to have low velocities at the bottom, high velocity at the top, and Bernoulli theorem will tell you that there is therefore higher pressure at the bottom and less pressure at the top, so there is actually pressure gradient, a force, trying to move the vortex up. So Fm is the Magnus force. And if you do it more carefully, you come up with this expression. So rho s would be the density of the superfluid, because it's the superfluid which matters here. Kappa is the quantum of circulation. S prime, remember, is a unit vector along the vortex, so perpendicular to the page here. And then we cross it with the velocity. Now, what matters is not an absolute velocity, but the relative velocity between the vortex line and the incoming superflow. Okay? The other force which may act on the line is the friction. Okay, so motivated by the experiments, mainly with second sound in rotating helium, that is the expression for the friction which was taught by Hall and Vinen. which Schwartz used. Now, in rotating helium, the vortices are straight. We know exactly in which direction they are aligned, and we know that there is a uniform density. So things are somewhat clear. It's a very good prototype, which helps a lot. So essentially, there was plenty of evidence that the force had two components. There was one transverse component, which is here, with the cross product, and one longitudinal, with a double cross product. You may say, why do you put two cross products? Just to make it more messy? Well, it turns out that this is done on purpose to essentially to take into account some experiments. Okay? So I don't want to spend time on that. So this is the expression of the force. So we recognize here the relative velocity between the superfluid and the normal fluid, and some coefficients, alpha and alpha prime, which are friction coefficients. They're the same B and B prime, already introduced by Hall and Vinen. And so you find in the literature either the use of alpha and alpha prime or B and B prime. Essentially, alpha prime is the transverse friction coefficient. Alpha is the actual friction coefficient. Alpha is what matters, is what makes the energy to be lost. Superfluid energy, which is put into the normal fluid and then dissipated by viscosity into heat. The effect of alpha prime is actually quite interesting. It's not a dissipation. It changes the inertia, however, and it was measured first by measuring the change in the frequency split of some resonant modes when you are in rotation. So it takes some effort to measure alpha prime, and actually it is a small quantity. Oh, I lost it. So keep in mind that the second coefficient, the transverse one, alpha prime, is often about an order of magnitude smaller than alpha, according to measurements. Okay? Right, then we have to think a bit more. So Vn would be the normal fluid velocity. In doing so, Schwartz assumed that the normal fluid is what is essentially imposed by the heater, plus the boundary condition, perhaps. That is not exactly correct, because in doing so, we neglect the effect which the vortex lines themselves have on the normal fluid. So I'll go to that later. What about Vs? Well, Vs, actually, the superfluid motion, the superfluid velocity, actually, can be thought as consisting of various parts. There is some kind of applied velocity, which is actually applied externally. We have a heater, a resistor, driving a current of flow. Or we have, perhaps in some experiments, some bellows or some pistons pushing the helium through. So that is applied. So it's given, okay? And that must be a potential flow by necessity. And then there is also another potential flow with singularities, which is the self-induced velocity of the superfluid. What is meant by this traditional name? It is the velocity field which the vortex filament or other vortex filaments induce at that location which we consider. Okay, because the vortex has a velocity field around it, so if it is bent, part of the vortex will induce a velocity in other parts. Or if there are more vortices around, will produce some effect. And how do we compute this self-induced velocity? Well, the answer is given by this. This is a classical formula from classical fluid mechanics, or if you want, from electromagnetism. That is how we compute a magnetic field given a current, but essentially the current is localized on delta functions, and we come up with this famous Biot-Savart integral. Okay? Oh, by the way, before I leave the point, there is a problem with this integral. Because you see that if you compute the velocity, self-induced velocity at the point position S, okay, R is a dummy variable, but if you compute it at the location S, which is what you need to move that bit of vortex which has been discretized, the integral will diverge. So you need to desingularize it. But there are techniques for doing that based on the fact that the vortex core is small but finite. So in any case, these equations can be solved for the velocity of the vortex line, VL, which is nothing but ds dt. So that is the equation which should be called the equation of Schwartz, because he derived it. So it's a recipe for computing the evolution of a vortex filament as a space curve. So what you see actually neatly is essentially three terms. So the first term is the superfluid velocity. That consists of the any flow applied from the outside, superflow applied from the outside by us, and then all the complicated flow induced by the vortices themselves. And then there are two terms which depend on the relative velocity of the normal fluid and superfluid at that location, which we want. So with those two parameters, alpha and alpha prime, there are dimensionless coefficients, typically less than 1. And they get bigger and bigger as you increase the temperature towards the lambda point. When the temperature is reduced below 1 Kelvin, they become very small and very difficult to measure. In fact, you can neglect them eventually. So in the limit of 0 temperature, the term with alpha and the term with alpha prime can be dropped, and you recover that ds dt is equal to Vs, which is Helmholtz theorem. A vortex moves with the flow. Okay? So, but we're not done, because Schwartz, since he tried to put together a computational, a computer code to work out what happens to many disordered vortex lines, immediately realized that there is a problem of what happens when vortices collide. And the answer was not in the experiments, because there was no idea about that, no evidence about that, but it was in Feynman's 1955 articles on the applications of quantum mechanics and this amazing conjecture of reconnections. So what Schwartz did was essentially apply the following algorithm in the simplified form which I present. So we have a blue vortex and a red vortex. We have discretization points, the black dots. We know each, the position at any time, each position, and we know that when vortices come sufficiently close to each other, somehow we need to switch the indices which relate one discretization point to the next. So this blue vortex and that red vortex will become two red-blue vortices. And things can be done slightly better, but not much better, because we don't have really much evidence. Clearly, this kind of method, which is Lagrangian, so we have moving discretization points rather than fixed Eulerian grid, contains this typical separation between the vortex points as the numerical resolution. Okay, so typically we set the numerical resolution, and then we need to add or subtract discretization points depending on the curvature. Okay, it's silly to keep too many discretization points, but we need enough when the curvature actually is very tight. Okay, the other thing to notice is that this model assumes the Biot-Savart law. So it comes from the incompressible Euler dynamics. So there are no sound waves at all. In fact, he did not, probably Schwartz never thought of sound waves. He knew about second sound and first sound, but he never thought of sound waves affecting things at this kind of length scale. And the other thing to notice and stress is that we assume that the normal fluid is given. Okay, so here it is again, so the use of our law. I just want to make some remarks. First is that actually this law, which is the classical law, can be derived, it has been derived from the Gross-Pitescu equation recently by Bustamante and Nazarenko. And the second is that it is actually what possibly what made Schwartz to go to work at IBM all his career, because you need a big computer. If you want to move, if you discretize your vortex configuration and you have 10 vortices, then to move at each time step, you have to look at what happens at the other 99 vortices. Okay, so you end up with a kind of n times n minus 1 operation. So essentially n square operation. So when you have a very large n, it requires a very big computer to do something, to produce a vortex tangle. So that was a limitation even at IBM in the 80s. And so Klaus came up with this solution, which is essentially this formula. He did. Nowadays, this formula is often referred to as the local induction approximation. It is an approximation of the Biot-Savart integral, which takes into account only the local contribution. So we're forgetting far-field effects. You can put it this way. It's how we regularize this integral. And there are things to notice. So here we estimated there is the local radius of curvature at the position which we desire, capital R, and the direction of this term is along the binormal. That's quite nice. It's quite interesting because the reason we have turbulence in our system, I think, is this. So if you imagine you have like a string and you pluck it in this direction, okay? So a vertical string, I pull it this way. It will move back along the normal direction. Okay? So it will actually try to go back to the rest position, which it will not reach unless there is a bit of damping. But if you do that to a vortex, it will not move back along the normal direction. It moves along the binormal direction. So it has actually a chance of going out to the plane where it was not before, of going and hit other vortices, making a mess, making reconnections. So somehow I think that the essence, well, it seems to me that a good part of the complications start here. Now, at that time, this law was not referred to as the local induction approximation, because the origin of this law is quite funny. Schwartz called it the Arms-Hammer approximation. There was a paper written in the 60s by two fluidynamicists for thin vortex filaments, that is where it comes from, called Mr. Arms and Mr. Hammer. And they wrote a paper in the physics of fluids and they published this. But actually, this law was actually discovered long before by somebody called Darius, published possibly in some Italian mathematics journal in the early 1900s. So it was the kind of school of mechanics of Ricci, Levi-Civita, and those people. Yep. Perhaps. So it's, it is a law which was constantly kind of written, forgotten, etc. Somehow, in the last, we converged to this name now, LIA. I don't know. Okay, that's for the history buffs. Now, what about the problem of the CPU time, which is n squared? Well, that is a serious problem. Let me explain physically why it's a serious problem. The difficulty with the local induction approximation at the place of the Biot-Savart law is that you end up with an algorithm which moves vortices according to that law, Schwartz equation, and performs reconnections. But as such, vortices don't see each other. What does it mean? Well, it depends. If you take a vortex ring, it's circular, you can actually use the local induction approximation and you get a very good estimate of the translational velocity because it depends on the curvature which you have in the formula. So there it seems to work fine. But take a structure like the vortex knots presented by Davide Proment this morning. So remember how a trefoil is made. So essentially it looks like a vortex ring because it's some kind of going around loop, but there are three lobes, essentially, trefoil. So those three lobes will actually try to rotate like this. But it was, remember, it was drawn on a torus. So if you look at carefully from the side, you see like two strands going around. So those two strands will actually attempt to rotate each other because they're going in the same direction. So the motion of the trefoil knot, which you've seen in the movie this morning, is actually complicated. There is a translational velocity. There is actually the lobes rotating, and there is this kind of internal twisting of the torus. Now, that internal twisting of the torus is not captured by the local induction approximation, okay, which captures only the translational motion because of the average curvature and the motion of the lobes. So you're missing some physics. So you want to do better, and you need to do something about the CPU problem. So the solution, which can be applied in some problems, but not all, is the following. This same problem, computational cost, which increases with n squared, is also there in Newtonian gravity, the oldest science, perhaps. Because if you want to consider, for example, the collapse of a galaxy, or galaxy colliding, for example, or the collapse of the solar system, so many particles coming together by gravity, you move each one. You know you apply Newton's law to each particle, and you end up with this problem. And there is, in the 80s, essentially algorithms were invented to speed up this calculation. So rather than a computational time which goes like n square, these two people invented a way of proceeding which is a bit like a Fourier transform. So it goes like log n, which is much better. And so that was implemented in the vortex dynamics, speeding up immensely computations. As I said, however, this is something which you can do if your configuration in general supports this approximation. So it must be rather isotropic, for example. So there are caveats. So that is what I wanted to say about the gross filament, the vortex filament method. Let's go now to the next level, which is the macroscopic level. So here, the guide is the original equations of Hall and Vinen, and also Bekarevich and Kalatnikov, okay? And if you want actually to see a mathematical derivation, I think the best paper is actually the paper by Hills and Roberts in a mathematical journal which you would not read normally. The Archive of Rational Mechanics and Applications, or something like that. So what they did, they extended, they used some basic assumptions. Essentially, it's the approach of the rational mechanics. They wrote the most general equations, then they tried to confine all the assumptions, and they came up with this. So it's a generalization of the Landaus equation with a continuum of vortex lines. So they had in mind, therefore, a system with lots and lots of vortices, which locally are somewhat polarized. So imagine this cube is a fluid parcel, mathematical fluid parcel, very tiny, and it contains a high density of vortices. So clearly, within this cube, you can count the vortices and define a vorticity vector in each direction using the quantum of circulation and simply the count of vortices crossing the area. So in this way, you can define a vorticity, a superfluid vorticity field. Okay? Now, this approach, however, would not describe a situation like in this picture. So here we have 4 vortices going out of the cube. So clearly, the vorticity field associated to these little cubelets is a vector which points like this. But what you do in a situation like this, where you have 2 vortices going up and 2 going down, you have vortex length, which will cause dissipation, but not a vorticity. There is no net rotation there. So clearly, the model fails when you face situations of this kind. It must be said that how Hall and Vinen came to this was by the study of rotating helium. So they had in mind, above all, the problem of the rotating container, essentially the vortex lattice, which we know. So the alignment of the vortices was sort of assumed. Okay? Yes? Well, you don't know, because you don't know really. The vorticity, the curl, you have a velocity field, you can compute the curl, and what does the curl describe? It assumes that essentially you are in this situation. So in the model, there is not the possibility of having lots of vortex length, which dissipates, without a vorticity. Okay? So in that sense, it fails. And we don't know, actually, we don't have a good judgment of this failure. In fact, the model has been used for turbulence, but we are on a kind of gray area. We don't know whether we can. Okay? Okay, so this is the Hall-Vinen equations. There is also a term which is needed. It's called the tension force, which you see in the superfluid equation. So it's based on the idea of the coarse-grained superfluid vorticity, a continuum of vortices. So essentially, the model fails when you actually take a fluid particle so small that you start counting vortices. You must actually look at the forest, the density of the vortices. Okay? So actually, this is the beauty of the entire mutual friction force, and it actually works very well. You can actually, when you apply it to rotating helium, it works very well, including the term with the tension. And essentially, it's the energy per length term which you need there. And there is your omega s, the vorticity of the superfluid. So it has been applied to the rotating lattice. and can be used to derive, for example, all sorts of nice things. Properties like, okay, let's not go into that. The rotating lattice like this. I think the model has been pushed consistently with the assumptions behind it. I think at the best for Taylor-Coed flow. Now, Taylor-Coed flow is the flow of a liquid between concentric rotating cylinders. It's a classical problem in fluid mechanics, famous for convincing people of that the no-slip boundary conditions are correct. So the work of G.I. Taylor in the 20s, the work of Chandrasekhar in the 60s. So if you have actually two cylinders, imagine rotating in a cylinder at small rotations, you have azimuthal flow, and you can actually ask your students, second-year students, to find a solution. It's very simple. And from the point of view of a superfluid, well, the vorticity is that vorticity for a continuum. So the whole Vinen equation will have essentially a uniform density of vortices, which are somewhat sketched here, pointing down, corresponding to this flow up. So then the good question in fluid mechanics is at which rotational velocity this azimuthal flow becomes unstable, and you generate on top of the azimuthal flow also Taylor vortices, like an m=0 pattern, mathematically very similar to Bénard convection. So, yes? For this particular case, yes, the boundary conditions is simply that there is no superfluid velocity into the boundary, so it can slip. Yeah. But the boundary condition, okay, boundary conditions are a bit of, you start going into the gray area. The model assumes there is a high density of vortices. So what you do with the model, which assumes a high density of vortices, when you reach the boundary where there are no vortices. Okay? The boundary conditions are not implied by the equations, are extra physical information. Okay? So there are all sorts of complications and essentially missing information. We don't have evidence from experiments enough. In fact, experiments will tell you that if you have this rotating lattice, you will actually you will have like the famous vortex lattice in rotating BCs. There is actually a missing layer of vortices near the boundary. There is a famous paper by Fetter on that. So how you take into account the missing layer with a model which assumes a continuum, it's not clear. So in any case, the prediction of a critical velocity is actually a very, very sharp, very strong test on some fluids equation because it's easy to miss it. I just make an example. If you do Bénard convection and compute, the problem of an infinite layer heated from below. So if the temperature gradient across the layer is large enough, you get convection rules. Mathematically, it can be mapped into this problem. And the critical Rayleigh number, the dimensionless measure of the temperature gradient, computed by Chandrasekhar is 1708. But if you use the wrong boundary conditions, which Chandrasekhar in his famous book of hydrodynamic stability discusses, you would get a critical Rayleigh number of 1650 or so. So it's a big difference, okay? And that would be actually, the wrong boundary conditions would be stress-free rather than no slip. So it's a very sensitive test. So the whole Vinen equation passed the test. Experiments done in helium showed this critical velocity, and they can be computed using these equations. And what is the vorticity field which you get? So in the Coed state, all the vortices are aligned. In the Taylor state, where there are these cells, essentially the vortices are bent. So the model works. But what about turbulence? Well, we can actually, when we have a turbulent flow, we can actually solve the same equations and drive it hard. So what's wrong? You will get solutions. What do they represent? What do the solutions represent? We don't really know. So we tried this years ago. So it was essentially the person doing this task was Emmanuel Levesque, who had a very good Navier-Stokes solver. He doubled the number of equations and in a periodic box. And we did not actually put in the full whole Vinen friction. We just simplified, because it makes no significant difference, to this form. So in essence, the friction contains a temperature-dependent coefficient alpha, together with rho divided by rho n, which depends on temperature, the quantum of circulation, the density of vortices, and the relative velocity of the two fluids. And this is the typical turbulence which was computed for the normal fluid and the superfluid. You see the regions of high entropy of the superfluid and normal fluid. So pretty much similar. And so we can tell that it works. We can predict results. There are some predictions which seem to work well, so something like the relation between essentially the drive, the mechanical drive of the system, the Reynolds number and the number of vortices, which is here simply represented by the density of the vortex lines. They seem to work. But whether it is true, for example, that the two entropies will, on the average, match, I'm not so sure. Perhaps, clearly, we need to do things of this kind more. In fact, they're doing, Emmanuel is actually running these things with better codes. But above all, experimental information is missing. Yeah. We never tried it at small Reynolds numbers because we need to assume, we need essentially the vorticity of the superfluid to be high enough that we can think that L is a continuum, a high density of vortices. Okay, so we never took this. So I don't know the answer to that question. Okay, so if we compare these models, what do we learn? So we have the Gross-Pitescu equation, which is a good model for atomic gases at low temperatures, but for helium, well, it's just qualitative. There are no rotons, for example. We can actually improve things. A big advantage of the Schwartz approach, the vortex filament model, is that you can put in the temperature which you want, and it comes in precisely with some knobs to turn, the friction coefficients, the density coefficients. But not in Gross-Pitescu. You need to make Gross-Pitescu temperature dependent. And this is actually quite interesting story. There are many approaches, stochastic projected truncated Gross-Pitescu equation. There is also this, which I put my hands into it, which is the Zaremba-Nikuni-Griffin formalism, which couples a modified Gross-Pitescu to a Boltzmann equation. Then there is the vortex filament model at mesoscales. There are no sound waves, so there is no way to lose energy in that fashion, acoustically, like you've seen this morning. The reconnections are done algorithmically, so we compute precisely what happens to vortices as they come together as far as we want to go, provided we make the discretization small. But we don't really want to go down to the angstrom scale. We like to stop sooner. So we compute the dynamics correctly, but at some point, the last point, when we cut and paste, it must be done by hand, algorithmically. Major problem is that it lacks the back reaction of the vortices on the normal fluid. So the normal fluid affects the vortices, but not vice versa. So it's not self-consistent. And the whole Vinen equations, it works provided there is sufficiently polarization of the vortices. So I want to give a look at the quantum Boltzmann plus Gross-Pitescu, because actually it gives an interesting result. So this is the case in which we have some kind of disc-shaped condensate in which there is one vortex, which you barely see there. You see that dot. So this vortex is going around, like Luca explained this morning. It perceives the density gradient, or the image, so it circles. But it is at finite temperature. So the orbit is a spiral, and it is more or less tight depending on the temperature, or better, depending on T over Tc. Okay? So in this series of pictures, you see the condensate, high density is in red, blue is 0. You see the vortex clearly, which is going around, spiraling, like you see there. It's interesting to look at the thermal atoms, what they do. So the thermal cloud is concentrated near the edges of the condensate, like you see here. But you notice that there is a mark here. There are more atoms in the core. So from this model says something which was imagined long time ago, that there is something in the core. It's not empty. Okay? Okay. And what about making the equation, the equation of Schwartz self-consistent? So what we need is a way of computing the normal fluid, which takes into account the vortices. So we need to imagine that there is some equation for a viscous fluid, which must be the Navier-Stokes equation, in which we add a term, which is the friction induced by the vortices. The vortices, however, are filaments, delta functions. Navier-Stokes, we like to solve it on a grid, typically. Okay? So we need to force Navier-Stokes on a grid. Now, that was attempted a long time ago, naively, and that was the result. So what you see here is the normal fluid kind of created by a moving vortex, essentially, which is in the middle and comes out to the page. So there is some kind of structure which is computed. But there is no experimental information on this. But perhaps nowadays, with the technique of putting hydrogen tracers and also unstable molecular tracers, essentially molecules of helium, ions of helium, which are much, much smaller than the micron-sized tracer, essentially it's one atom. It's possible to actually perhaps go down to these scales, and there is perhaps the technique exists to go and see whether this is true, that there is a disturbance, essentially. And what is actually what would be the effect? We don't know. It could be a small disturbance which is cute, it's some kind of dipole, okay, but it's not important. But it may be the key, because it may actually destabilize the profile of the normal fluid, which has just been seen using this technique. So there are lots of things. And I think at this time, I think I'll stop. And I thank you for listening to me.